So the end point of the last lecture was that I roughly sketched how to define superstring theory in a way that is parallel to bosonic string. So you remember the starting point, the point where we got to was the idea that one could imagine having sort of a super worksheet mapped into space-time. And after gauge fixing, one ends up with some sort of a super conformal theory. So it's a theory that behaves reasonably under this sort of transformations. Okay. And so one main property of this superconformal field theory is that it has a stress tensor, traceless stress tensor, and it has a supercurrent, which in these conformal gauge is denoted usually as G and G bar. So, roughly speaking, like T is something like a, so the T, remember, transforms up to central charge, like something with a two Z indices, so like a square of the Jacobian, plus some correction proportional to the central charge. And this guy has a power of 3/2 of the Jacobian. So this is, if you want, in terms of the eigenvalues of delta and delta bar, the behavior under scaling and rotations. These guys have quantum number 2, 0, and 0, 2. And these guys have quantum numbers 3/2, 0, and 0, 3/2. Now, the same way as we didn't really study conformal field theories in our lectures, we will not study superconformal field theories particularly. Rather, I'm going to just look at the simplest example, the one that is relevant for studying superstrings moving in flat space, which is the theory which is the supersymmetric generalization of a free scalar. So it's a theory which includes a free scalar and a free fermion. Both massless. So, intuitively, the range that I'm trying to build is sort of a super scalar, a scalar which is a function of superspace. And when you expand it, you get a free scalar. Then you get something like that. Then in principle, there is also something like this. So if you look at the transformations under diffeomorphisms, you see that essentially when you do a coordinate transformation, a standard coordinate transformation for z, theta gets multiplied by the square root of the Jacobian. Probably the power. There must have been a minus sign over there, but it doesn't matter. So because X was transforming a scalar field, had no powers to the Jacobian, the result is that this guy gets the power of the Jacobian. So psi transforms like that, which is kind of like the square root of how the current transforms. Yes.
What's that? There at the end?
Then there is a final guy, which actually drops out. So the equations of motion for x classically are del bar x equal to 0. Equation of motion for psi are del bar psi equal to 0 and del psi bar equal to 0. And the equation of motion for f is f equal to 0. So we're going to forget about f promptly.
So I just had a question, going back to kind of the start. Why do we need superstrings as opposed to the bosonic string? Like,
bosonic string is a tachyon, so it's garbage as a physical theory. So the superstrings, I don't know, at this moment it's just an attempt to find another theory of strings that might be more interesting. But precisely, we want a theory of strings which has fermions. If nothing else, right, in nature we see fermions. Bosonic string only has bosons. So a theory of strings that would be interesting for describing the universe should have fermions too. So that I mimicked the construction of this string theory on the one-dimensional theory which describes one fermion. And we'll see what kind of excitations we get in the string theory.
I guess so. I mean, we'll still have the bosonic modes. So sort of schematically, how do the tachyons cancel out? Like, how do we not have the tachyon modes?
We'll see. So psi and psi bar together are the two modes of a free fermion. They're like the two chiral halves of a free fermion. Now, usually, when you work with fermions, I used to see gamma matrices all over the place. In conformal gauge, there is a way to just fix your gamma matrices with some very convenient values and just forget about them, so that the Dirac equation, for example, becomes something very simple. And the action becomes also something very simple. So, while normally a fermion is something which transforms as in a specific way under Lorentz transformations which involve gamma matrices. When you look at conformal transformations on the plane only, all that defines a fermion is just this square root of the Jacobian put in front of it. So a free fermion is just some guy of dimension 1/2, 0. And as you see from the Lagrangian, quantizing the free fermion is not going to be any harder than quantizing the ghosts. It's a first order action. So it's rather simple to work with. Pretty much. So remember we expanded the free boson in modes. And then we quantized it by something like that. for the free fermion, again, we're going to expand it in modes. And write down some commutation relations. The stress tensor is roughly something like this. And then there is this supercurrent, which looks like that. These are pretty much all the only bilinears you can write. So, roughly speaking, the supersymmetry transformations map x into psi and psi into dx. Okay? So they typically map G into T. So if you act, so either you send x to psi and you get this term, or you act on psi, transform into dx, and you get this term. Forget about the factors of 1/2 that I'm having floating around anyway. I guess I should probably have 1/2 here. So, okay, so the basic ingredients are relatively easy. Understand, and using this one we can just understand roughly the superstring spectrum. Besides this, there is of course ghosts. Sorry, perhaps Vn was not the best possible choice of the symbol. I was supposed to subside. So there is some B and C. There is some beta and gamma. I essentially will say nothing about them. Just know that roughly that they exist. And then there is a BRST charge. Which very roughly looks like that. Now, when you quantize the fermions on the cylinder, there is a very basic choice you need to make. And to decide if these fermions are going to be periodic or anti-periodic. Now, you might ask why. Why should I worry about this? After all, for the boson, I just took it periodic and I was happy. The reason is that because of this square root of the Jacobian, when you change coordinate systems, you actually might end up switching the periodicity of your fermions. In particular, imagine I'm trying to match a cylinder to the plane with the usual exponential map. That means that the fermion on the plane, sorry, the fermion on the cylinder is related to the fermion on the plane, or something like that. You see, this is going to go to minus itself as you rotate the phase, the imaginary part of S, which means that something that is periodic on the plane will become antiperiodic on the cylinder and vice versa. In particular, for example, if you're looking at the state operator map, things like which are standard operators like the identity, say, psi, etc. all map to states on the cylinder. So these are operators with the property that if you bring a fermion around them, it goes back to itself. But because of that, it means that if you bring the fermion around the corresponding state, it goes to minus itself. So these ones become antiperiodic states which are an antiperiodic fermions. So this sector of the Hilbert space is called the NS sector. Conversely, if you want to study states which seem to be more normal, which seems to leave your fermion periodic around the circle. So these are really guys that send psi of sigma equals to 2 pi equal to minus psi of sigma equals to 0. If you want to look instead at states that are periodic, the property that psi of sigma equal to 2 pi equal to psi of 0, which is called the Ramon sector. This must map to operators which make the fermion antiperiodic. So these must be operators with the property that psi z, psi to the 2 pi I, z equal to minus psi of z in the presence of the operator. So if you rotate the psi around the operator, it must go back to minus itself. These kind of operators are called twist fields. And it might take a little bit to get used to them. So there are operators which are defined in a theory, not by putting some of your elementary fields in the path integral, but rather by modifying the path integral. So a twist field is an operator that is inserted in a calculation by saying I do the path integral over fermions which are antiperiodic around this operator. Now, have you guys seen the Ising model? That's good. What do you remember of the Ising model? So, I mean, have you seen the solution of the Ising model? So, in the Ising model, you have this system of fermions. I don't know if the camera can actually see you. I assume yes. Right? And perhaps at some point I told you that the Ising model is equivalent to theory of free fermions. Or not. I'm not sure. Possibly not. So in the Ising model, you have these sort of elementary variables, right? Which can be plus minus 1. Right? And right, if you remember, there is a sort of phase diagram, right? The function of the temperature. If you're at high temperature, your spins are disordered. If you have a low temperature, they are ordered. In the middle, there's a second order phase transition, which actually, so it gives you a theory which has scale invariance. It's actually a conformal field theory. And it's essentially a theory, has the same properties of theory of free fermions. Now, recognizing the free fermions in this picture is usually not easy. The reason is that in terms of the theory of free fermions, the operator sigma, which is the wave of this, which measures this, the average, locally the average of these spins, is a twist field for the fermion. But if you want to define the fermion operator inside this, in this model, you actually need to sort of change the Hamiltonian. So you can consider pictures like that where you have your Hamiltonian, sum of sigma I, sigma j for ij neighbors. And you can imagine adding some line going through your lattice and switching the sign of the interaction for all the edges which are intersecting the line. So if here there is an interaction between edges, we call it ij, jij. Usually your j is 1 everywhere. But you can put j equal to -1 at some of the links. Now the position of this line really actually doesn't really matter. Meaning, if I want to move this line from here to here, for example, so that these links become normal and this link become reversed. Perhaps you can see that you just need to flip the sign of this thing. So if you send sigma I to minus sigma I, all the sign of the interaction of all the edges which go into the point switches. So this sort of adding this line does really nothing to your Hamiltonian. You can move this line around. But if this line ends somewhere, then there is something interesting going on there. So this is a way to create a local operator in your Asim model, which is not made out of the elementary fields. And out of this kind of local operators, you can actually build those free fermions that solve the model. Conversely, from the point of view of the free fermion, you can start with the theory of free fermion and define an operator by doing a path integral over all configuration of, essentially, roughly speaking, you're sort of adding a line with the property that psi goes to minus itself every time you cross it. Because the location of this line doesn't matter. But if the line ends, that matters. So the properties of the theory here are different. There is really a local operator inserted here. You can ask what are the properties of these local operators. And the way you do it is exactly by going back to the cylinder and seeing what happens. This tells you so you figure out things like the eigenvalues of L0, or how the first tensor acts on it, and that tells you what are the properties of this operator. Now, doing calculations in the presence of twist fields can be interesting. So if you just have, say, if I have a bunch of twist fields and a bunch of fermions, because the free fermion theory is still a free theory, still covered by a Gaussian path integral, I can still sort of use the Wick theorem and replace the fermions with some 2-point functions. I need to compute the 2-point function, the Green's function, in the presence of these twist operators, which might take some effort. But then I still have the problem of computing the correlation function after I've got rid of all the fermions. And doing this from the point of view of path integral is very challenging. You would need to essentially compute the determinant. You're computing a Gaussian integral. So the answer, if you don't have any insertion of psi, is just the determinant of this del bar operator, of the kinetic term. But it's a kinetic term in the presence of this antiperiodic twist fields, or these antiperiodic boundary conditions, which makes the calculation rather challenging. Luckily, there are other ways based on conformal field theory, which allow you to answer these sort of questions. There are differential equations satisfied by these correlation functions, which can be used to solve, to compute them. That's just to say that even if I introduce these extra complicated looking ingredients, everything remains fully calculable. Although perhaps free field theory is not anymore the best way to do it. Really, knowing conformal field theory becomes important. So, but for computing things on the cylinder, we don't need any of these. So all we need to do is to just Fourier expand psi and apply our commutation relations. Now, if I have Neveu-Schwarz boundary conditions, which meant antiperiodic states for the fermion, I'm going to expand my fermion in Fourier modes, with an index that is shifted by a half. Let me just write it very roughly, like that. Okay? I'm not sure that normalizations are exactly the correct ones, but this is okay. So with the modes for this fermion carry an half integral index. The anti-commutation relations are still written like that, but n lives in the integral shifted by half. So I can write it as psi n with n belonging to z plus 1/2. Or I can just write it as psi n plus 1/2. Well, let's make it like that. So the Fourier modes I have are things like psi 1/2, psi minus 1/2, psi 3/2, psi minus 3/2, etc. And the anti-commute. And each of these raises the energy by the corresponding amount. So psi minus 1/2 will raise the energy by 1/2. And there are also, of course, psi bars. Which do the same. On the other hand, on the Ramond sector, I'm going to expand my fermion in standard integral Fourier modes. So I have modes which are integer valued. And then everything is more or less like this, but so I have psi 1 and psi minus 1, commute, etc. But crucially, I also have psi 0. Now, to understand the effect of this psi 0 is actually useful to keep track of all the fermions we have in the game. So let me put back the Lorentz indices, which I had suppressed. Now, this should remind you something we saw yesterday. Essentially telling you that the psi naughts are gamma matrices. So in the Ramond sector, I have two sets of gamma matrices acting on my states. So it means that the basic states of my in the Ramond sector will have to sit in some spinor representation of the Lorentz group. Okay? So perhaps for now I can denote them like that, where A is a spinor index acted upon the psi naughts, and A bar acted upon the psi naught bar.
Will there be a factor of 2?
Whatever. So this is really important. So these are space-time spinors. Okay. So superstring theory has space-time spinors as fermions. So the psi naughts are playing exactly the same role as the. I mean, this was the main reason we added psi to the theory of a single particle to get gamma matrices. When I do it in string theory, I actually get too many reaches. I get two sets of gamma matrices and two spinors. So you might say, oh, wait, this is actually not a fermion. Well, the point is that here what I call NS is really something like an NS bar, right? I took NS antiperiodic boundary conditions for both the psis and the psi bars. This I should probably call an RR because I have Ramond boundary conditions for both the holomorphic and anti-holomorphic psis. In principle, nothing prevents me from considering situations where the psis are periodic and the psi bars are antiperiodic. So I could consider something like an NSR sector where I have psi 1/2, etc., but I have psi bar 0.
So why are like psi 1 not? Oh, I guess the other question is why do we only have psi 0 as the gamma matrices when we have the same anti-commutation relations for the other ones?
Well, so see, when I try to define a vacuum for this guy, so the vacuum has to be healed by, say, psi 1, and then you build on top, you build on it by psi minus 1. But the properties of the vacuum do not depend much on what you're doing here. You define your vacuum however you want, and then these guys act upon it to create new states. And the other guys act on it. These guys kill the vacuum, and they act on other states by these anti-commutation relations. On the other hand, here the zero modes really map the vacuum among themselves. So the structure of the zero modes, the quantum numbers carried by zero modes, are much more important in understanding what are the properties of the vacuum. Now, see, in principle, even for the theory of free bosons, okay, you could have told me, wait, you said that my vacua are labeled by P and that's scalars, and then I act on them with my oscillators to make things with indices. But why didn't I just add some indices by hand to this guy? Why didn't I say that I have a bunch of 10 vacuums, 76 vacua rotated by my Lorentz transformations? Now, the point is that we don't want, so if you just did the quantum mechanics, okay, so Lorentz transformation was just some operator that you pick defined arbitrarily in quantum mechanics. This would be perfectly okay. On the other hand, in a quantum field theory, your Lorentz transformations are not something that you get at random. It's something you build as the integral of a locally conserved current. So there is local current of Lorentz transformations, and then the charge comes from integrating the current over the whole space. So the point is that your Lorentz current would be something like, I don't know, x dx, x mu, dx mu. Okay. And plus possibly some renormalization. Okay, so to define a problem in quantum theory, we'll need some point splitting or something like that to normal order this. But it's important, all counter terms, all modifications should have to be local. You cannot do a modification which depends on where you're living. Because of that, the expression for the actual Lorentz generators is essentially fixed. You know, it'll be something like, I don't know, I don't remember it by heart, but something like that. Okay? Actually, call it 1 over. Because of that, the action of the Lorentz generators on the vacuum is not something that is you're free to decide. This Lorentz generator acting on the vacuum gives you 0. So the vacuum is a scalar. Or gives you, actually, more precisely, it's going to give you something like P mu, P nu, of course. Well, P mu is nu. But anyway, so it only acts on this P label. So the correct answer to your question here is that I can write the current for the Lorentz transformations. I can normal order them, regularize them. I get something like some psi n, mu, psi minus n, mu, something like that. And then I act them on the vacuum. And these guys don't contribute at all when I'm acting on the vacuum. But these ones do. And this reduces exactly to the expression of the Lorentz generator built out of gamma matrices. So this is the full answer of why you get a very specific representation for your ground states in terms of the 0 modes. So here we get just a ground state for the fermions. No fancy Lorentz indices. But then we get something with 2 Lorentz indices. Here we get something with a single Lorentz index, spinor index, and the same here. And then you build on them with fermions. Now, if you remember, I anticipated that this theory of superstrings lives in 10 dimensions. So these are 10-dimensional spinors. If I get time at the end of the lecture, I'll have a very quick review of how spinor representations are built in various representations. I'm not sure I'll be able to get to that. But anyway, so these are 32-dimensional spinors, and they can split into a positive and negative chirality spinors. When you act with psi on a positive chirality, you get a negative chirality, and vice versa. Now, at this point, we can essentially start building up the spectrum of the superstring theory, except for the information about the Casimir energy of the ground states, which I cannot compute for you because it has contribution from the super ghosts and from the ghosts. Now, notice that depending on the sector you are in, Ramond or Neville-Schwartz, the supercurrent will be periodic or antiperiodic. But your BRC charge better just current better be periodic, otherwise you couldn't define the conserved charge as zero mode. So gamma ends up having the same periodicity as your fermions. So the change in periodicity for gamma and for the fermions affects the Casimir energy. So all in all, the Casimir energies, or if you want again, the not again values of this guy are -1/2, including the effect of the superghosts, the ghosts, the bosons, and the fermions. While for these guys, there is no Casimir energy. The way to understand this is actually that because in this sector, the supercurrent is periodic, you can define the zero mode of the supercurrent, which is a supersymmetry transformation. And there's a, there is a well, in general, is almost a theorem that every time you have supersymmetry, something that some supercharge squares to the Hamiltonian, your ground states typically have zero. Anyway, let's take it as a fact. So we can start computing things. So we want to find things that are killed by LNs and by L0, possibly modulo null states, and also killed by G n. So the first class of states we can consider are just momentum modes for the free bosons with no oscillators, neither bosonic nor fermionic. And these guys are going to give you tachyon. It's still here, hasn't gone anywhere. Next, we can try to compensate this -1/2 by acting with oscillators instead of changing the moment, setting the momentum to be 1. So I can do something like that. This gives me massless states. And as you can guess, this looks more or less the same thing that we got in bosonic string. Some guy with 2 indices. Just that it's built out of the psi's instead of being built out of the a's. And this gives you the usual graviton plus B field plus dilaton. At some point you could just say, okay, why do we do all of this just to get another tachyon?
What's this condition you have with the G sub n?
G and, sorry, just the positive Fourier modes of
So the Ln condition comes from the constraints on the stress tensor, right?
That's right.
Where does this?
From the constraints, so the constraint of the stress tensor was the equation of motion for the metric.
That's right.
This, so set T to 0.
Right.
Then there is another equation of motion, G to Z equal to 0, which comes from the gravitino.
Okay.
Roughly speaking, these conditions are required. You need 2 sets of conditions because you have 2 sets of dangerous modes. There is the time-like scalar, but also the time-like fermion.
So you want Ln to be 0 for n greater than 0, right? And L0 you want.
Well, I'm including here the effect of all the ghosts. So because I defined L0 0 equal to -1/2.
Okay.
Sorry, I well, okay, it's the same as in the bosonic string. There is a Casimir energy.
So N0 on P is P squared over 2 minus 1/2.
Yes,
That's how it works.
that's right. That's right. Now, so this is a tachyon. That looks bad. Luckily, there is something here that we did not have in the bosonic string, which is called something called the fermion number. So I can define from a number operator with a property that anti-commutes with all the fermions. Okay. The action of the fermions can be, this could be, for example, one of the Lorentz generators. It can be built out of the Lorentz generators. It's just a rotation of pi in a lot of planes. But actually, because the supercharge has terms like this, so the BST charge has terms like this, and you want this to be useful operator in your theory, which in particular means leave the supercharge invariant.
Is that supposed to be an anti-commutational?
Yes. So, thank you. You need to do something like that for gamma too. And for beta. So pretty much this operator sort of recognizes the things that are there in superstrings and not in bosonic strings. And then I can define another fermion operator, like antelomorphic fermion operator, which only anti-commutes with the antelomorphic fermions. Okay. Now, so this is a conserved quantum number, and it behaves well with a BST charge, which means that when I have some sort of scattering process of strings, this quantum number will be preserved. Now, it turns out that because of these conditions, the ground state of the ghosts have a funny value of this quantum number. So, in particular, minus 1 to the f t is actually minus t. So this guy has quantum numbers under minus 1 to the f and minus 1 to the f bar, which are minus and minus. On the other hand, these guys are obtained by acting with another fermion on that. So this is quantum numbers plus and plus. Which means that when you scatter these guys together, you never create a tachyon. So you can consistently drop it. This is called the GSO projection. The GSO projection tells you you should only keep things that are invariant under the action of this minus 1 to the x. And magically, there's no more tachyon. The theory makes sense. And everything can work. So this sort of GSO projection gives you something that's called type 2 superstring theory. There are 2 variants of type 2 depending on how you define the action of minus 1 to the f on the Ramon sectors. So, as I mentioned, there are 2 chiralities. you can decompose your index. Whatever you get in sort of indices, you can decompose it into either positive or negative chirality guys. And they're going to have minus 1 to the f equal to, say, 1 or minus 1, or vice versa. Have so one of the two choices gives you type A, and the other gives you type B. Should A and should B superstring theory. So depending on this choice, the GSO projection ends up throwing away slightly different combinations of these Ramon-Ramon sector fields.
Sorry, are we saying that there is no way to build a state that has the Fermion number -1 even with acting with more psi work?
No. I'm just saying that if you take through these string states
Right,
and you scatter them,
can we build different combinations? I can look at the rest of my spectrum as well, no?
Sure. So there will be a big spectrum.
And none of them.
Everything is massive. Some have plus plus, some have minus minus, and
Okay.
we only keep the plus plus. Now, what do we do on this side? So on this side, we have our ground states. And as I said, L0, there is no Casimir energy on the side, on the Ramon side. So we only need to adjust things on the left, on the holomorphic side, anti-holomorphic side. You can do something like that. With p square equal to 0. And then the GSO projection will keep only one of the two chiralities here. I guess with the notations I have there, it's probably alpha naught. No. Yes. Well, whatever. So what is this state? It's a state which carries a spinor and a vector index. It's massless. And it actually has an interesting gauge symmetry if you look at the null states. So if you put a polarization of sort, you have a gauge, you have null states of the form of this sort. So it turns out that this state is precisely a space-time gravity. So it's a partner of the graviton for supersymmetric theory, which is supersymmetric in space-time. This is a little bit surprising, right? Our starting point was super worldsheet, but normal space-time. But then the theory presents us with a gravitino. There's actually a theorem that matches when you have whenever you have in quantum field theory a spin-through state massless, which looks like a graviton. It is a graviton. It couples to everything like a graviton. Your theory must be diffeomorphism invariant. Then there's another theorem that tells you whenever you sort of spin 3/2 state, massless with a gauge symmetry, has to be a gravitino. Your theory has to be a supersymmetric theory with super diffeomorphism invariant, coupled to supergravity. So, a bit magically, the superstring theory becomes a theory becomes the supersymmetric theory in space-time. Now, the precise type of supersymmetry depends on which gravitinos your theory has. So, for example, depending here on your choice type 2A or type 2B, your gravitinos will be of the same type, of the same chirality, or of opposite chirality. In type 2A, you have gravitinos of opposite chirality. In type 2B, you have gravitinos of the same chirality. And so this means that a low-energy theory will be some supergravity theory in 10 dimensions, with gravitinos either of the same chirality or the opposite chirality. So these supergravity theories were known, are known, and the Lagrange and their interactions are just fixed by supersymmetry. So this sort of allows you to write down the low energy effective action for superstring theory, just because you know it's supergravity. Or I guess in principle you could also do it as I was describing in some lecture, by starting with some superstring moving in the background and doing a normalization group flow. Finally, you get some states from the Ramon-Ramon sector. As you can imagine here, I don't need to add anything. This is already a massless state, which carries two spinor indices. You can always convert two spinor indices into space standard Lorentz indices by using Gram matrices. So these states are going to give you a whole bunch of bosonic fields in spacetime. They're called Ramon-Ramon fields. They're just a bunch of forms. They're generalizations of gauge fields with various number of indices, which couple to D-branes. So D-branes in this supersymmetric theory, in the superstring theories, are sources for these Ramon fields. And precisely because they are sources for these Ramon fields, while normal strings are not sources of Ramon fields, that tells you that these D-branes will have to be stable, because they carry charges. We cannot go anywhere else. They cannot decay to strings. So D-branes become so D-branes also have no tachyon if they have the correct dimensionality. I'm not going to go into details. But so they exist and make sense in the superstring theory, and they're a very, very important ingredient. Indeed, perhaps you can turn things around. If somebody had told you that this sort of superstring theory exists, that is a generalization of supergravity, where you have some big dynamical objects coupled to the fields of supergravity. In principle, all these dynamical objects are on the same footing. It just happens that one of those objects becomes light when you turn off the coupling of the string of your theory, and all the other objects become very heavy. And so there is some limit in which your theory can be described in perturbation theory by fluctuations of these, or the dynamics of these light objects, which are the strings. But typically in these supergravity theories, there are many, many corners in your space of couplings in which different objects might become light. And so in principle, one can set up different perturbation theories based on different objects. Sometimes these objects are again strings. And so this gives rise to very important dualities that relate different string theories, such that in some values, for some regions of the parameter space, your theory can be described as some string theory. Some other region parameter space can be described like a different string theory in terms of different ingredients. When one is weakly coupled, the other is strongly coupled, and vice versa. That's the last thing I should perhaps mention. there is a very close relation between the fact that we kill the tachyon with this gesso projection and the fact that we have a gravitino. See, when you have, here we did everything on the cylinder. We felt free to have Ramon, NS, periodic, antiperiodic, whatever. But once you start transforming these states into operators and putting these operators on your worksheet, I don't know, here I want to put my Ramon state, here I want to put my graviton, psi bar. Okay. Well, I might start worrying. This Ramon field makes some of the things antiperiodic and some periodic. For example, around this operator, psi is going to be antiperiodic, and psi bar is going to be periodic. So my correlation function does not look single-valued anymore, which surely is going to create troubles in calculations. So although I can make a big list of states, not all of these states in the list can actually simultaneously exist in the same theory. They must correspond to operators which are local with respect to each other. It can be, they get no phases when transported around each other. And it just so happens that this gesso projection exactly ensures that that's the case. So, for example, if I want to keep the tachyon, if I decided not to throw away the tachyon, then I could not keep this guy. Because that this guy is antiperiodic around the tachyon. Vice versa, if I want my gravitino, then I have to throw away the tachyon. So this is another way to understand why the gesso projection. You can, in principle, define theories in which you throw away the gravitino and you keep the tachyon. They're called type 0 theories. They are as sick as bosonic strings. In principle, they can be defined. Finally, there is one more thing that you can do to define interesting superstrings. So here I had my z and z bar, I had the theta and theta bar. So I had psi and psi bar. In principle, you can do something intermediate between bosonic string and this full superstring, which you only add psi's and not psi bars. This is still enough to give you fermions, it's still enough to give you a gravitino, although only one instead of two, and to define some interesting theories which are called heterotic string theories.
With regards to the coupling, you were saying you can tune the coupling and get duality.
Yes.
Do we have? I mean, ultimately, the goal of the program was to, in low energy limit, actually produce my regular QFT. Does that give me anything I can say about what my coupling should actually be? Like, does it give me fix my numbers?
Well, which QFT do you want?
Well, I guess I would want standard model, right?
Yes. So if you understand the model clearly, string theory in 10 dimensions is not going to do well for you.
Okay.
What you can do is to take some of these chunks, some of this stuff, and replace it with something else. As long as you're while invariant, you're fine. But while invariance, you're fine. So you can take 4x's psi bars and something else. The list of the possible something else is enormous because there are a lot of conformal field theories. And on top of that, it's likely that our world is not described by perturbative string theory. In the sense, we don't see any dilaton, as far as we know. So on top of that, you need to take those theories and move away from weak coupling. There might be further non-perturbative effects, which one has to take into account. So the short answer is we don't know how to get precisely our world. If you play the very basic games, you can get kind of interesting words, typically with a lot of supersymmetry because that way things are more tractable. For example, there's something called Calabi-Yau compactification, which gives you a four-dimensional supergravity theory with 8 supersymmetries, 8 supercharges, which is way too much to make contact with our universe. But well, you can put a heterotic string on the Calabi-Yau, then things get better. So a heterotic string typically, at least in the beginning, was seen much more promising because it has non-abelian gauge fields built in, without even putting any D-branes. But then people discovered D-branes, and they realized they can find non-abelian gauge fields in type 2 as well. And then there are dualities which relate all sorts of theories among themselves. So what can I say? There seem to be a possibly large space of vacua for string theory. So all of these different modifications of superstring theory are presumably connected among themselves. So it's still one theory, but it has many, many different manifestations. And we do not understand the dynamics of the theory well enough to know if some of these are preferred to others. I think for a while the dream was that by some magic, we would just end up with one possibility and would end up being the standard model. For example, when people started studying ways to replace scalars with something else, these Calabi-House, in the beginning they thought maybe there is only a few Calabi-House, and then they found a lot. The alternative is that maybe all of these possibilities are valid, so that string theory can describe almost everything. I would say that at the moment, the original dream, which was to bootstrap yourself all the way from our energies all the way to the Planck scale by saying there is a unique way to complete quantum gravity into something, it's probably lost. So one of the lessons of string theory has been very harsh. It's easy. There is plenty of ways to get a theory of quantum gravity. They come a dime at a dozen for the dozen. What can I say? It's sad, but it might mean that actually we cannot bootstrap. Perhaps the most pessimistic possibility is that the only way to know what's going on at the Planck scale is actually to scatter something at the Planck scale. I mean, philosophically, it's a valid possibility. I don't really know what to add to it. We can surely keep searching. I mean, the biggest possible discovery I can imagine in this context is to find some other theory, which is not string theory, and it has the same resilience. Some other theory which is robust, makes sense at every energy, and cannot be deformed into back to string theory. But we have not been very lucky with that. So, for example, ADS-50 offers in principle a way to construct theories of quantum gravity by starting from some quantum field theories in one less dimension. Now, the first example of holography of ADS-50 came from string theory. There's a theory called N equals 4 super Mills. It's a four-dimensional gauge theory, the maximally supersymmetric generalization of Young-Mills theory. And because of string theory, we knew that the holographic dual was one of the supergravity theories, was a superstring theory. Right. Then you can look for other quantum field theories and say, maybe I'll be lucky. Maybe the holographic dual of these other quantum field theories will be some other theory of quantum gravity which is not string theory. And at some point, people discovered other theories which had really nothing to do with this N equals 4 super Mills, and which have an holographic dual. But again, it turned out to be a string theory, or an M theory, which is a variant of string theory. It might be that, I mean, one might take this as an indication that if you try to do things with supersymmetry, you're probably always going to end up with string theory. It's not a proof, of course. One can, keep trying to list quantum field theories, and I would like to stress, although the way that is usually presented, holography is tied up to string theory in the sense they would say, okay, I take a gauge theory of matrices, I do a large N, I get this sort of 't Hooft expansion I discussed yesterday. I interpret the Feynman diagrams as surfaces, then this becomes a string theory. In this other example I mentioned, this is called a BGM theory. For some values of the parameters, this is not true. So there is no reason for which, and indeed the holographic dual is M theory. It's not string theory. It's a theory of stuff which is not strings, but it's still connected to string theory. So I don't know would be a good strategy to find such a theory, alternatives to string theory. They might exist. It would be very nice to find them. But even so, it would likely just lengthen even more the list of possible ways to get a UV completion of something that looks like our universe. So at the moment, string theory does not give us UV completion of precisely our universe. It might or not. We are not strong enough to verify that's the case. But it surely gives to the UV completion of a lot of universes which don't look that different from ours. Maybe they're a bit more supersymmetric. Fine. But they have graviton, gauge fields, matter fields, fermions. What can I say? Any questions?
If not, let's thank Davide for the question.